There were limitations to the Bohr model. Number one, it only worked for hydrogen-like atoms, which is hydrogen, of course, and any other atom that has just one electron. It's an ion of the various atoms. It's based on an assumption that accelerating charges do not emit electromagnetic radiation if they are in specific orbits. There's no reason to say that other than it made the model work. Also, the model did a great job of predicting the frequencies of the photons that are emitted when electrons change orbits, but it does not predict their intensities. Bohr, of course, kept doing work on his model. Many other physicists joined in, and this all helped transition the explanation of the atomic phenomena into a more complete quantum world. Let's look at electrons and light together next. In 1923, Arthur Compton scattered X-rays, and this thing here where it says incident photon, these are X-rays. He scattered them off of a graphite surface, which is called a target right there, and he observed that the wavelength of the scattered X-rays increased, and this was later named the Compton Shift. So we've got the X-ray coming here, it hits a target, an electron gets booted out over there, and here is the scattered photon. So he's postulating now that the photon is a particle and it has energy E equals hf. It collides elastically with the electron. Now, you might recall from mechanics that momentum and kinetic energy are conserved in an elastic collision. So that means the scattered photon down here, here's the scattered photon, it's going to have less energy than the original one. Some of its energy went over to the electron. So, since this has lower energy, that means it has a lower frequency, but it also has a longer wavelength. In deriving the equation for how much the photon's wavelength is shifted, and remember we're dealing with the photon as a particle now, you have to use Einstein's equation for the relativistic energy of a particle. Now, we haven't covered that yet, but let's just take that as truth because it is. The energy squared of a particle equals its momentum squared times the speed of light squared plus its mass squared times the speed of light to the fourth. Now, the mass of a photon is zero. It's a massless particle, so this term here goes away, and we take the square root of both sides, and the energy of this photon is its momentum times the speed of light. We divide through by c, we substitute in hf for the energy, and then we replace c over f with lambda, and we find out that the momentum of the photon is h over lambda. What's really interesting about that is we have a massless particle now that has momentum. And if you recall from mechanics, momentum for mechanical objects, large objects, was described as mass times velocity. And yet here we have a photon with no mass, but it does have momentum. After solving the conservation of energy and momentum equations, and you have to use the relativistic versions of these equations since photons move at the speed of light, the following angular dependent equation was derived. Now, don't worry about the math, it's a bit beyond this course, but you will see it again perhaps in an AP course or in college. The wavelength shift, which is the final wavelength minus the initial, is h over the mass of the electron times the speed of light times 1 minus cosine theta, and theta right here is the angle that the scattered photon makes with the horizontal line that continues. The incident photon came in like this, so had it not been scattered it would have kept going straight, but this scattering angle here is how much the photon was deflected by the electron, and of course the electron went off in this direction. With all these incredible theories and experiments in the first 25 years of the 20th century, it's interesting to note that the neutron's existence, was not proven until James Chadwick demonstrated its properties in 1932. Back in 1920, Ernest Rutherford did propose that a neutral particle, which we now know to be the neutron, with a mass on the order of a proton existed to account for the atomic mass measurements of atoms. Experiments were performed before Chadwick, so after Rutherford came up with this, there were experiments, but they mistakenly believed that the neutrons that they saw were really gamma rays or even protons. So they saw them, they just didn't know they were neutrons. They thought they were gamma rays or even protons. Why do you think it took so long to discover neutrons? The neutron is neutral. There is no charge. So it was impossible to detect it via electric and magnetic field manipulations that made it possible to discover the electron. What Chadwick did is he placed a small quantity of radioactive polonium in an evacuated chamber, a vacuum, and it decayed by emitting alpha rays, which of course are just helium nuclei, helium without their electrons. This then struck a beryllium target. Neutrons were emitted from this reaction and were found to have both the correct mass and a neutral charge, absence of charge. So the function of neutrons, and also protons in the nucleus, there's the strong nuclear force that keeps the nuclei together. This strong nuclear force balances the repulsive Coulomb force that is felt between the positively charged protons. We'll talk about that more later in the nuclear physics course, the nuclear physics section of this course. The neutron is neutral. There is no charge. So it was impossible to detect it via electric and magnetic field manipulations that made it possible to discover the electron. What Chadwick did is he placed a small quantity of radioactive polonium in an evacuated chamber, a vacuum, and it decayed by emitting alpha rays, which of course are just helium nuclei, helium without their electrons. This then struck a beryllium target. Neutrons were emitted from this reaction and were found to have both the correct mass and a neutral charge, absence of charge. So the function of neutrons, and also protons in the nucleus, there's the strong nuclear force that keeps the nuclei together. This strong nuclear force balances the repulsive Coulomb force that is felt between the positively charged protons. We'll talk about that more later in the nuclear physics course, the nuclear physics section of this course.